there, it's Professor Shannon Gracey. Today we'll be covering section 5.7 from the calculus text by Larson and Edwards, and this covers inverse trig functions for integration. So you'll either have a result of an inverse trig function after finding an indefinite integral, or you will have them as part of the integrand, which is actually really awesome because then you know what your u substitution is going to be. So there's a couple things that we're going to want to review so that you can be all up to date. First of all, let's go over what we covered during our last lesson. So go ahead and pause the movie and warm it on up. On your mark, get set, go! You can do it! Okay, let's see how you did. So if we differentiate both sides with respect to x, we will have d dx of y and then d dx of this. D dx of y is beautiful, dy dx, and then that's going to be equal to, so we'll take it a little slow to make sure you're good to go on this. We'll have d dx of arctangent at x over 2, and then minus d dx of our let's write it like this. We can bring out this constant 1/2 and then times d dx of quantity x squared plus 4 raised to the minus 1. Okay, so far? Awesome. Okay, so dy dx will equal to, you're going to differentiate with respect to x the inside of the arctangent, and that's all going to be over 1 plus the inside squared. And continuing, we will have minus 1/2 times, this is just our regular power rule. Remember, you're differentiating. So you're going to get negative 1 times our something to the negative 2 times d dx of our something using the, what was that rule called? The chain rule, right? So here's our something. And then moving right along, we will have dy dx is equal to, good, we'll have 1/2 over 1 plus x squared over 4 minus 1/2 times, let's see, we'll do the minus is plus, right? And then we'll have our x squared, I'll write that as a fraction. So we have really 1 over, here we go. So we're going to have 1 over 2 times quantity x squared plus 4 squared. And then we're going to multiply that by the derivative of that inside, which is 2x. So now let's check it out. Do you see that, I'm going to leave it like this because, well, I'll divide out that 2. Why not? So those 2's will divide out. So now we just need to clean this up. So we'll have dy dx is equal to, we're going to have 1 over 2 times, getting a common denominator with the 1 plus x squared over 4, we would end up with 4 plus x squared over 4. And then this one will give us plus x over x squared plus 4, the quantity squared. And then continuing, this 2 divides out some of this 4, and that 2 is going to jump up, and we need to get a common denominator. So we're going to need to multiply this guy by x squared plus 4 over x squared plus 4, and the other one's going to be fine. So this will lead us to dy dx is equal to 2x squared plus 8, so I multiplied that 2 through, that jumped up to the numerator, plus x all over x squared plus 4, the quantity squared. And I believe that we've got a prime trinomial there, so let's just write it as dy dx is equal to 2x squared plus x plus 8 all over x squared plus 4, the quantity squared, and we're all done. Good so far? Awesome. All right, so this next guy, what do we have to do here? When we differentiate both sides with respect to x, we're going to have something that some parts of it will need to be differentiated good implicitly, right? So here we go. We're going to have the derivative with respect to x of that product xy, because that's the inside of our arctangent function. That'll be divided by 1 plus xy, the quantity squared, so that's our left side. And that'll be equal to the derivative with respect to x of the sum x plus y, and that'll be over the square root of 1 minus x plus y, the quantity squared. Okay, so far? Good, good. All right, so this is going to be, we'll do the derivatives first. So we're going to end up with d dx of x, so now we're using the product rule, right, times y plus x times d dx of y all over 1 plus xy, the quantity squared. That's going to be equal to d dx of x plus d dx of y. And that's all over the square root of 1 minus quantity x plus y squared. Cool so far? Awesome. Okay, so now completing these derivatives, we'll have 1 times y plus x times dy dx all over 1 plus xy, the quantity squared, is equal to 1 plus dy dx, and that's going to be all over the square root of 1 minus quantity x plus y squared. Okay? All right, so now, here we go. Now it's all about simplifying. So let's go ahead and we'll clear out those denominators. So what's going to happen is we'll end up with y. Oh, that's looking a little funny. Sorry about that, guys. Y plus x times dy dx. That's going to be multiplied to the square root of 1 minus x plus y, the quantity squared, when we clear the denominators. And then we'll have that's equal to 1 plus dy dx times 1 plus quantity xy squared. So now it's just a matter of isolating dy dx. So this will give us y times root 1 minus quantity x plus y squared plus dy dx times x times root 1 minus quantity x plus y squared is equal to 1 plus xy, the quantity squared, plus dy dx plus dy dx times quantity xy squared. Okay, so moving right along, let's get the dy dx's on the same side. So we've got more of the dy dx's on the right side, so I'll get the terms without dy dx on the left and with dy dx on the right. So this will give us y times the square root of 1 minus quantity x plus y squared, and then I'll be subtracting, let's see what we have, subtracting a 1 and subtracting quantity xy squared, and then that's going to be equal to dy dx plus dy dx times quantity xy squared, and then minus dy dx times x times the square root of 1 minus x plus y, the quantity squared. So let me just make sure. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, I didn't forget anything. All right, so continuing, we will have y times root 1 minus x plus y, the quantity squared, minus 1 minus xy, the quantity squared, is equal to, I'm factoring out a dy dx, and we'll have a 1 plus xy, the quantity squared, minus x times the square root of 1 minus x plus y, the quantity squared. All right, so finally dividing by the factors that we, the terms that we factored out from dy dx, we will end up with y times the square root of 1 minus x plus y, the quantity squared, minus 1 minus xy, the quantity squared, all over 1 plus xy, the quantity squared, minus x times the square root of 1 minus x plus y, the quantity squared, is all equal to dy dx. Okay? And that's good enough. Well, how'd you do on that guy? Did you at least get the differentiation right? If you didn't get the simplification, was the differentiation done right? Well, good, right? So that's awesome if you got the whole thing, but these can be difficult problems. So now we're going to be utilizing the completing the square skill set for this section. So what do you guys remember how to do this? Let's see. So let's see how you did. This can be written as negative. So factor out a negative. You want the x squared alone. And then we still want to have the x term. But the constant we don't want to have as part of that. So do you see this as equivalent? I've just switched it around a little. If you distributed through the negative, you'd get the same thing that we started with on the left? Good. Now, effectively, what we need to do is we need to add 0 to this, all right? So if you recall, you're going to be adding half of that middle term, the coefficient to the middle term, squared. Now, I know that that negative is going to go away, but trust me, if you write it like that, you know exactly what's going to go, what your binomial is going to be that's being squared. Now, what did I really adjust this by? I really adjusted it by inside a positive 4, but do you see there's this negative on the outside? There's a negative here, right? So basically, I've added negative 4, so I have to add positive 4 to balance it out. So if we multiplied all this out and simplified it, we get what we originally started with, okay? Now, what we're going to do, if you did it like I did here, what's going to happen is whatever's in that parenthesis that's being squared is going to go down here for your binomial sum or difference that's being squared. And then we'll have plus 7 over here. So the way that it'll, if we kind of pretty it up a little, we'll end up with this, okay? So these are equivalent and in a format that'll be helpful to us. Okay, so next up, we've got this one. So again, sorry about that, we're going to need to take the 2 away, or factor out the 2, so we have a coefficient of 1 in front of our x squared. So that'll give us x squared minus 3x, and then I have my plus 9 still hanging out. So now I'm adding negative 3/2 squared, right? So let's see how I really adjusted this. So when I square that, do you see I'll get 9/4, and 2 times 9/4 is 9/2. So I've added 9/2, so I have to take away 9/2 to balance it out. So this will give us 2 times quantity x minus 3/2 squared. And then if I get a common denominator, this will end up being plus 9/2. And we're done. All right? Okay, so remember from our last lecture in 5.6, what did we notice about the derivatives of the inverse trig functions? There were basically three pairs, right, which differed by a factor of -1. So the beauty of this is that with our integrals that involve inverse trig functions, so basically they end up having a result of an inverse trig function, we just use 3 of those, one of each of those pairs to give us just 3 formulas, okay? So the trick here is going to be, well, first of all, learning how to utilize these formulas, all right? And secondly, what we are going to need to do is we're going to need to be able to strategize, because a lot of times what happens at this point in a person's calculus life is they're so excited about the new formulas, when you get a result of a natural log or, an inverse trig function or something. What'll happen is you'll want to have that result all the time, whereas you have to remember your skills from before, right? So let's see what we have going on here, and go from there, okay? So look at part A, right? And let's look at these formulas and let's see if any of them might apply. So here, can I write this in the format of the other ones? So I'm kind of looking at that arcsecant formula, right? And really, I guess if you wanted to, you could say, x is equal to u, so dx would be equal to du. You see that? And you also have an a, right? So your a in this case is going to be equal to, just 1. So basically what we're looking at here is the integral of du. And again, you do not have to do a u sub for this one, but just to kind of look at matching up the formulas, we'll do that. So then we had u squared minus 1 squared. And do you see that that does indeed match our formula for the result of an arc secant? So let's take a look at what we've got. So dx was equal to du. Our u was just x. And our a was 1. Okay? All right, so now what would we have? We would end up with this result like we were saying. So that would be equal to, let me box that off. So this would be equal to 1 over a, so 1 over 1, arc secant at absolute u over a, which was 1, plus c. Okay, so again, our a was, whoops, wrong color. Our a was here, okay, and then our u is here. So now, back substituting, we're going to have, this is equal to arc secant at absolute x plus c. Okay? All right, so now let's take a look at this guy. All right? What do we have going on with this one? I mean, if you look back at those formulas, I don't think any of them would quite work, right? And, if you wear a size 8 shoe, you don't want to jam yourself into a size 6 shoe, right? So here, let's just take a look. Let's kind of do what we used to do when we first learned about this. Remember, we would often rewrite it as a product if we had a rational expression. Sorry, the screen decides to freak out every so often. Okay, so then this would be x squared minus 1 to the negative 1/2 dx. So, what do you think we should do with this guy? Beautiful. If we just try a u sub and let u equal to x squared minus 1, du dx would be perfect, 2x. And then isolating dx, we would get du over 2x. Right? So let's see if it all worked out. This will give us the integral of x times u to the negative 1/2, and in for dx we have du over 2x. And then, let's see, our u was this one. And remember, if you do a change of variables, you got to get rid of all those x's. You can't just factor them out because u is a function of x. So fortunately, the x is divided out, and we end up with 1/2 times the integral of u to the negative 1/2 du. And that is just our general power rule. 1/2 times u to the negative 1/2 plus 1, remember the old rule, over negative 1/2 plus 1 plus c. Remember that just because it was in the denominator doesn't mean it'll have a result of a natural log function, right? Okay, so continuing, we will have 1/2 times u to the positive 1/2, and then that's going to be divided by 1/2 plus c. So that's just going to give us, the 1/2s will divide each other out, right? And that's going to give us our u to the 1/2 plus c. And what was u? Perfect. X squared minus 1 to the positive 1/2 plus c. Now, those problems looked pretty darn similar, didn't they? Part of your difficulty with this stuff is a lot of things will look very similar, so you have to really strategize. And don't be afraid, you know, if something doesn't work out okay, then hey, try something else. Don't freak out. Use pencil. Okay, what about this guy? If I tried a u sub, what would happen? I mean, I'd say u is 1 minus x squared, right? Du dx is negative 2x. And then isolating dx, I would end up with du over negative 2x, right? And let's see what happens, right? This would give me the integral of dx was du over 2x over u to the 1/2, right? Oh, and that was negative 2x. Negative 2x. And so basically you'd have this going on, right? So whoops, dx was all this, right? Our u was this. And cleaning that up, it would be, this is equal to negative 1/2 times the integral of u to the negative 1/2 times x to the negative 1 times du. You see that there's an issue there? Crap, right? So that strategy didn't work, right? U sub didn't work. So what else do we do? I mean, you know, if you haven't memorized them yet, that's fine. You go and you look at your formula list, and you'll need to memorize everything here. And you'll see, oh, hey, what about formula number 1, right? So this one, actually, once you know that formula, is going to be a real easy problem, isn't it? So, okay, that's why we use pencil, right? We can erase this stuff. That strategy didn't work. On an exam, right, you would just put a line through it so your teacher could see what your train of thought was, right? And then work it somewhere else. And then we go through and we say, oh, that's exactly our, so here we would say, oh, again, x is u, dx therefore would be du, and a, again, is 1, isn't it? So we could rewrite this guy as the integral of du over the square root of 1 squared minus u squared. And then it will match your formula for the a squared, the 1 over, you know, dx or du over square root of a squared minus u squared perfectly. Let's finish this. This guy was our a, and then our u is just x. So again, you did not need to do a u substitution for this, but just to kind of show you the pattern here. So this is just going to give us, good, arc sine at u Now, is that all it is, arcsine at u? Remember, there was those over a things, so you always want to double check, right? But, so it's arcsine at u over a plus c. And our a was 1. And that will give us arcsine at x plus c. Okay? So u over a. Okay, so moving right along, right? Again, we have something very similar here, right? We're going to have, actually this is a different batch of similar problems, right? So here, let's see what we have. I mean, if we go along, what do we usually do? We'd say something like, this is the integral of, x to the negative 1 times natural log at x to the negative 1, that whole quantity, times dx. And so what did we say about the natural log function when it's part of the integrand? That was a good thing, right? Because you know that u has to equal to natural log at x, because we didn't have a formula that gave us the integral of natural log at x dx, right? So du dx is equal to 1 over x, and then dx would equal to x times du. So let's see what happens when we plug that stuff in. We'll get the integral of x to the negative 1 times u to the negative 1, and then in for dx we have x times du. So here was our u, and dx is x du. And then, keeping our fingers crossed, what happens when you multiply x to the negative 1 to x? What are you going to get? Good, you'll get the integral of x to the 0 times u to the negative 1 du. And what is x to the 0? 1. So then we just have the integral of u to the negative 1 du, and what does that have a result of? Perfect. Natural log at absolute u plus c. Back substituting, what do we get? Good. Natural log at absolute natural log at x, I know it looks funny, plus c. And you're done. Good job. All right. So now, what do you think we might want to try here? And, feel free to pause the movie and try these on your own. So here, again, if you rewrite it all as a product, you'd have the integral of x to the negative 1, quantity natural log at x squared, dx. So if we did our u sub as perfect natural log at x, du dx is going to be one over x, and isolating dx, again, we're going to get x times du. It looks real similar to that last one, doesn't it? Well, let's see what happens. So this will be the integral of x to the minus 1 times u squared times x du. Again, x to the negative 1 times x is going to be x to the 0, which is 1. So we get the integral of u squared du. So this is where these two problems are going to differ, right? Because this is just going to be our general power rule, right? Where we go u to the 2 plus 1 over 2 plus 1 plus c, which gives us u cubed over 3 plus c. Now what was our u? Perfect. Natural log at x cubed over 3 plus c. Now, be careful. A lot of times at this point of the game, people want to get fancy, right? And they want to use, properties of logs to divide out that 3. Can you do that? Well, let's check it out. So this will just be a little side note. So, natural log at x, the quantity cubed, is exactly equal to natural log at x multiplied to itself 3 times. Right? There's no property of logs, right, for the product of 3 logs. Now, if you have natural log at x cubed, where it's not the natural log being cubed, it's what's inside the log, this is natural log at x times x times x, which is natural log at x plus natural log at x plus natural log at x by properties of logs, which gives you 3 of those natural log at x's, right? So notice the difference between these. Which case do we have? We have this one right here, don't we? Which means we can't use any properties of logs on that. Okay? All right. So next up, what about this guy? If you look at your formula list, there is no formula for this, right? I mean, if you did a u sub, and you said, oh, u is natural log at x, du dx is equal to 1 over x, so dx is equal to x times du, and then you wrote all that in, you'd have the integral of u times x du, right, which would be something that you can't get rid of the x, right? This x won't divide out. And you can't just bring it to the front of the integral, because then you wouldn't have completely, found the integral. So basically, this problem here is going to be for your Calc 2 class, and you use a technique called integration by parts. Integral. Okay? And that's in Calculus 2. Okay, so now let's look at some techniques that we can use. So for this guy, again, it's always good to sort of visualize a u substitution. But do you notice that here, if you said u is x squared plus 4x plus 13, your du dx would be 2x plus 4, and we don't have that, right? If it was just the constant, we could do something, but it's not. So here, what we would do is we would say, okay, let's complete this square, right? So complete the square. So when we complete the square, we'll have x squared plus 4x plus 13 equals. So x squared plus 4x, and then, actually there's not going to be enough room, sorry. So we'll get the x squared plus the 4x by each other, leave a space, and then plus 13. And remember, we need to add 0 to this. So here I'd be adding positive 2 squared. And so I have to, subtract 2 squared, which is 4. And then I'll end up with x plus, 2, the quantity squared, plus 9. Good so far? Awesome. So now let's take a look. We've got we completed the square. So when you go back here and you say, okay, right, this will be equivalent to the integral of dx over, and then if you kind of switch them around, you'll have 9 plus x plus 2, the quantity squared. So is that looking like anything interesting? Good. It's looking like our arctangent result, right? So let's just kind of sort this out. After completing the square, we can say, okay, well, our u would be x plus 2. du dx is what? 1. So dx is just du. And remember that a was required to be greater than 0, so positive. So basically I'd get a squared is 9, and just taking our positive root, we would get a is 3. Okay, so far? All right, so putting it all together, let's see what we've got. So this will be the integral of du over 3 squared plus u squared. And this is all how it all shook out here. dx was equal to du. X plus 2 is equal to u. And 3 is equal to our a. All right, so now let's see what we've got going on. This is going to give us a result of, so what was that formula? Dun, 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 dun. 1 over a, right? 1 over a, arctangent at u over a plus c. Was that number 3? So we get 1 over a, which was 3, times arctangent at u over a, which was 3, plus c. And that gives us 1/3 times arctangent at x plus 2 over 3 plus c. So our u was x plus 2, and our a, again, is the 3. Okay? And we're done. How you doing so far? Awesome. Okay, so next up, we've got this situation. So what do you think about this guy? It kind of looks like our arcsecant result, doesn't it? Because if we did a straight up u sub, we do u is x to the 4th minus 4, and we'd need a 4x cubed, so we don't have an x cubed there. So let's check it out. I'm thinking this formula, right? I'm thinking of the integral of du over u times u squared minus a squared under the radical equals 1 over a arc secant absolute u over a plus c. That's what I'm thinking of, okay? So this is the evil plan, okay? So now, coming back over here, do you see we could write this as dx over x times the square root of x squared squared, right, minus 2 squared. So what would we do then? Good, we'd have u is equal to x squared, du dx would be 2x. So isolating dx, we'd have du over what? 2x. So let's see what we've got, right? This may or may not work. Plugging everything, oh, and then what was our a was 2. So plugging everything in, let's see what we would get. This would be the integral of dx over, or du rather, sorry, over 2x divided by x times the integral, or I'm sorry, the square root of u squared minus 2 squared, right? So this would be the integral of. The 2 would come out in terms of the 1/2, right? Oh, let me show you what's matching up here. So this is our dx. This is our u, and our a was 2. Right? So it's looking a little bit scary, right? But, you know, keep going. Sometimes it works out fine. So this would be 1/2 times du over x squared times the square root of u squared minus 2 squared. But what was u? U was x squared, right? So here we go. We'll have 1/2 times the integral of du over u times the integral of u squared minus 2 squared. So it looks like it's going to work out just fine. So here, x squared, if you remember from over here, is equal to u. And now we've got our arcsecant result. So this will give us a result of 1/2 times 1 over a, which was 2, right? Times arcsecant at the absolute value of u over a, which was 2, plus c. Now, plugging back, substituting, we'll have 1/4 times arcsecant at absolute x squared over 2 plus c. But now, is x squared ever negative? No, it's not, right? So you'll have 1/4 times arcsecant at x squared over 2 plus c, and we're done. So that was something where we got something that was in the form, you know, looked like it could be in the form of the result for an inverse trig, for an inverse trig result, but we had to also do a u substitution, right? So we had a little bit of trickiness there. All right, so what would you strategize for this guy? Well, this one sort of seems to be crying out for a completing the square, right? So let's try to complete the square on this and then see how it shakes out. So, negative x squared plus 4x equals negative. I'm factoring out the negative, so we'd have inside the parentheses minus 4x, leaving a space, right? So here we'd be adding negative 2 squared And so negative 2 squared is 4, but if you multiply by that negative outside, it's negative 4. So you have to add 4 to be adding 0. So now this is going to give us 4 minus the quantity x minus 2 squared, right? And hey, isn't that 2 squared minus x minus 2 quantity squared? So let's see what we should do over here. So if we bring the 2 outside the integral, we'll have dx over the square root of 2 squared minus x minus 2 squared. And that seems to be good. It'll have an inverse sine result, right? So our u will be x minus 2, du dx will be 1, so dx is equal to du, and our a is equal to 2. Okay, so far? All right, so continuing, we will have 2 times the integral of du over the square root of 2 squared minus u squared. So this all lined up. This was our u, this was our a, and then dx was equal to du. All right, so this gives us a result of, good, 2 times, good, arc sine at u over a plus c. So we'll have 2 times arc sine at our u, which was x minus 2 over 2, because that was our a, plus c. And we are good to go. And then this is how it all matched up. And this was our a. Okay? All right, let's see what's next. Okay, so for this guy, we've got a little bit going on here, right? A little bit going on here. So when I see a rational expression, I think about, oh, could I divide? Well, no, because the degree of the denominator is greater than the degree of the numerator, right? So now what should we think about? Well, a lot of you guys might have looked at, hey, what if we did a u sub, right? And what if we said u was x squared plus 2x plus 2, du dx would be 2x plus 2. That's real close to 2x minus 5, isn't it? So dx, if I isolated dx, I would have du over 2x plus 2. Well, let's play around with that, right? Because I might be able to do a little something with that. All right, so let's see what we got. So if I did something tricky here, like let's say I did this. Let's say I said I'm going to have the integral of 2x minus 5, right? And to get a positive 2, do you see I'd have to add 7, right? But to balance it, what do you have to do? You got to also subtract 7, so you're effectively adding 0. and that'll be all over x squared plus 2x plus 2 with respect to x. Now you're probably thinking, you're crazy, that's not really going to work. But check this out. We'll get the integral of 2x plus 2 if I look at the negative 5 plus 7 minus 7 all over x squared plus 2x plus 2 with respect to x. Now, I'm kind of looking down at that denominator and I'm thinking if I had a constant over that, I could complete the square and it would be an arctangent result, right? And if I have that 2x plus 2, then I'll have just a u sub. So this is going to end up being, if I split the integral, I'll have 2x plus 2 over x squared plus 2x plus 2 dx minus the integral of 7 over x squared plus 2x plus 2 with respect to x. Good so far? Okay, so the second integral is going to require us to complete the square, right? On the second integral. Right? So when we do that, we'd have x squared plus 2x plus 2 equals x squared plus 2x plus 2. We're going to be adding 1 squared, so we'll have to, subtract 1. And that's going to give us x plus 1, the quantity squared, plus 1. And 1 is the same as 1 squared, right? Okay, so we've got that going on for the second one. And this guy, remember, is going to be, this stuff here is going to be for this integral. So a u sub on the first one. So let's check it out. This will give us the integral of 2x plus 2 over u, and then dx was du over 2x plus 2. So on this first integral, dx was du over 2x plus 2, and our u was the x squared plus 2x plus 2. And check that out. That works out beautifully, right? Because we can divide out these 2x plus 2's, and we're going to end up with the integral of 1 over u du. But don't forget, we still have this second integral going on, right? So let's work on that guy, right? So we can bring the 7 out, right? And we'll have dx over 1 squared plus x plus 1, the quantity squared. So over here, if I said, I don't want to confuse you with too many substitutions, but if we said w is x plus 1, dw dx would just be 1, so dx would equal to dw, and our a would just be 1. And this is for that second integral. Okay, so let's check it out. We would have minus 7 times the integral of dw over 1 squared plus u squared. Nope, sorry. W squared. Okay? So dx was equal to dw. Our w substitution is the x plus 1, and our a is the 1. So now we're getting there, guys. This is going to end up being perfect. Natural log at absolute u is the result of the first integral minus 7 times 1 over a arctangent at w over a plus c. So here was our a, and we have our w. Okay, so, and actually, you know what I should have done? I should have done the w in a different color, because that's what I did in the u. So my u's from the first one are here, right? And then we'll do w in, I don't know which color. Hopefully this will show up okay. This is our w sub. Alright, so then this will give us the result of natural log at absolute u was x squared plus 2x plus 2, and then minus 7 times arctangent at x plus 1 plus c. And this was our w, and this here was our u from the first one. All right, so that one's kind of a little on the tricky side, but that's okay. It's like a puzzle, right? It's our version of Sudoku. All right, so here we go. What do you think about this guy? Why don't you try to do this guy on your own? See how it goes. Okay, so again, I'm thinking, hey, you know, this looks like a potential complete the square, u sub type of thing. So I'm going to do this. I'm going to say I'm going to complete the square first. Because in my mind, I looked at to see if we could do, you know, a u sub where u was equal to the integrand, or the, rather the u is equal to the radicand, right? The 9 plus 8x squared minus x to the 4th, but I don't have enough of those x's there. So when we complete the square, we'll have negative x to the 4th plus 8x squared plus 9 equals, factoring out our negative, we'll have x to the 4th minus 8x squared, leaving a space, we have our plus 9, and so adding negative 4 squared, right, that's positive 16, but it turns negative from the negative outside, so we really add 16 in order to add 0. So now what we'll have is 25 from the 9 plus 16 minus x squared minus 4, the quantity squared. Okay, so far? So that looks promising because we could let u equal to x squared. Du dx would be 2x. Isolating dx, we would have du over 2x, and our a would equal to, good, 5, because we have that 25, so this would be 5 squared minus x squared minus 4, the quantity squared. All right, let's see how this one shakes out. So we will have, this will be the integral of x over the square root of 5 squared minus what? u minus 4, the quantity squared. Good so far? All right, so now what was in for dx? Good. Dx was equal to du divided by 2x. So, got this going on here. Our a is the 5, and then u is in for our x squared. Okay? So, let's make sure we got rid of all those x's. So do you see, whoops, this x divides out this one, and we will have the integral of, or 1/2 we can pull out, and then we'll have a du over the square root of 5 squared minus quantity u minus 4 squared. Now, if you need to, you can make another substitution, right? Call it a w substitution. But do you see that u minus 4, when you differentiate, if you let w equal u minus 4, I mean dw du would just equal to 1, right? So I guess it just sort of depends on how many u subs you want to do. Me personally, I would see that I would have my result. But for those of you that, you know, need a little extra, we would have like a second substitution. So if we let w equal to u minus 4, dw du would be equal to 1. So du would equal to dw, right? And then then you'd rewrite it as 1/2 times the integral of dw over the square root of something squared, right? 5 squared minus something else squared, which is now our w squared. And this gives us an arc sine result, right? So, here we go. This would end up being 1/2 times arc sine at, good, w over 5 plus c. Now you got to back substitute all this stuff. So you'd have 1/2 arc sine. What was w? W was u minus 4 over a, which was 5, and then plus c. But what was u? U was x squared. Good. So that would give us 1/2 times arc sine at x squared minus 4 over 5 plus c. And you're finally done. So our u was x squared, right? Our w was u minus 4, okay? And I think we got everything else we needed. Okay, let's see what we have next. Okay, so now we have a definite integral. So what do you think we ought to do for this one? Well, if we thought about it as the integral from 1 to 3 of 1 over root x times 1 squared plus root x squared dx, is that equivalent to what we started with? Yep, as soon as I do that parenthesis there. Okay, so that means that my u would be root x, and du dx is going to be equal to 1 over 2 root x. So isolating dx will have 2 root x times du, and our a is going to be 1. So let's see how all this shakes out. What else are we going to have to do? Good, we have limits of integration, right, that we got to take care of. So u at 1 is equal to the square root of 1, which is 1, and u evaluated at 3 is the square root of 3. Okay, so let's get it all put in there. So this would be the integral from 1 to the square root of 3, because we need this in terms of u. Now we would have 1 over root x times 1 squared plus u squared, and in for dx we would have, wait, what was it? It was 2 times root x times du. So our a is the 1, and u is the root x, dx is 2 times root x du, and let's see what happens next. Do you see that the root x's divide out? And remember that our limits of integration we got by evaluating the limits for x in terms of what we let u equal to. Okay, so here we go. This will give us 2 times the integral from 1 to root 3 of 1 over 1 squared plus u squared du. So this will give us 2 times 1 over 1 arctangent at u over 1, and that's evaluated from u equal to 1 to u equal to root 3. So this was our a, and we still have our u. And we don't need to change it back because we changed our limits of integration. So let me just clean it up. This is 2 times arctangent at u, evaluated from u is 1 to u is root 3. So we will get 2 times arctangent at root 3 minus arctangent at 1, and arctangent at root 3 is what? At what angle input does the tangent function have an output of root 3? That'll be good, pi over 3. And arctangent at 1, beautiful, pi over 4. So, getting it pretty, we can have a common denominator of 12, and this would be 4 pi minus 3 pi. The 2 divides out some of the 12, and at the end of the day, we'll have, perfect, pi over 6. Cool? Awesome. All right, so next up, another definite integral. So let's see how we do for this guy. All right, Let's see how you did. So here, again, I'm seeing kind of an arctangent potential, right? Just like here, you had a situation where you could write something in a squared plus u squared under the radical, or I'm sorry, in the denominator with no radical. So do you see how we could do 1 squared plus sine x, the quantity squared? So what does that mean? That means that u would equal to sine at x, du dx would equal to cosine at x, and isolating dx, we would have du over cosine at x, and our a, again, would be 1. Now we have limits of integration, so u at 0 is sine at 0, right, which is 0, and u at pi over 2 is sine at pi over 2, which is 1. So now we have that all set. And let's plug it all in. So we'll have the integral from 0 to 1 cosine at x over 1 squared plus u squared, and in for dx we have du over cosine at x. Oops. And again, our limits came from over here. Okay. So now, let's see what happens. Fortunately, these cosine at x's divide out, and we'll have the integral from 0 to 1, and then we'll have du over 1 squared plus u squared. So that's going to give us arc 1 over 1, because a is 1, arctangent at u over 1, evaluated from u is 0 to u is 1. Cleaning it up, we'll have arctangent at u, evaluated from u equal to 0 to u equal to 1, which gives us arctangent at 1 minus arctangent at 0, which is pi over 4 minus 0, good, which is pi over 4, and we are done. Good so far? Awesome. And now we are on to an application. So here we want to find the area of this region bound by these graphs. So remember, with area, the area is equal to, whoops, sorry about that. Area is equivalent to the definite integral as long as the function values are positive. So do you see that the numerator is always positive and the denominator is always positive? So the area will be equivalent to, good, the definite integral from 0 to natural log at root 3, right? And then we have 4e to the x over 1 plus e to the 2x dx. So let's play around with this a little bit, right? Here we've got, we could rewrite this as our area is equal to the integral from 0 to natural log at root 3, and the 4 GC can come out, and we'll have e to the x over 1 plus e to the 2x is e to the x, the quantity squared. Good so far? So now let's try this out. Let's try doing a u sub where u is e to the x. So what is du dx? Perfect. E to the x. And then that means that dx will be du over e to the x. Changing our limits of integration, u at 0 will be equal to e to the 0, which is 1, and u evaluated at natural log at root 3 will be equal to e raised to the natural log at root 3. And remember, we are evaluating the natural exponential function at the natural logarithmic function, so we just get what's inside the log out. Okay? All right, so our area will be equal to 4 times the integral of e to the 0 was 1, e to the natural log root 3 was root 3, and we'll have e to the x over 1 squared plus u squared, and then in for dx we had du over e to the x. And I think I forgot to say over here that a would be equal to 1. So, let's see how it all shook out. So this du over e to the x was our dx. Our u was the e to the x. Our a is 1. And our limits of integration came about from evaluating the integral, or the limits for x, right, in our u sub. All right, so let's see what happened. The e to the x's divide out, so that's good. And so we'll have the area is 4 times the integral from 1 to root 3 of du over 1 squared plus u squared. So yet another, sorry there's so many arctangent results, our area will be 4 times 1 over 1, because 1 is our a, arctangent at u over 1, evaluated from u equal to 1 to u equal to root 3. So this was our a, and then our u, right, stays because we changed our limits of integration, right? And so here we go. The area, cleaning it up, will just be 4 times arctangent at u, evaluated from u equals 1 to u equals root 3. So we will get our area is 4 times arctangent at root 3 minus arctangent at 1. So the area will be 4 times, what was arctangent at root 3 again? Good, pi over 3 minus pi over 4. So getting a common denominator, we'll have this here. So our area will be equal to 4 divides out sum of the 12. We'll get pi over 3 of a square unit. Actually, that would be square units, barely. All right. Okay. So have a fabulous rest of your day. Bye.